Welcome, Rich. Thanks for joining us.
All right, thanks, Ethan. Yeah, I like giving web access because I feel like, it's just like people are just kind of sitting in my office looking at my screen. Although, I guess you guys might be able to squeeze in here. It might be a little tight. Anyway, I'm going to be talking about catalog-driven reproducible workflows for ocean science. And on the abstract, there was a longer title that involved something about sea level. But I'm not going to talk about that because something more interesting came along to talk about that it's still a reproducible workflow for ocean science. But I wanted to mention right off the bat that I work for the USGS, who is sponsoring my involvement with the Integrated Ocean Observing System, or otherwise known as IOOS. I'll tell you a little bit more about that in a second. And I've been doing this work with Felipe Fernandez in Brazil, and he is being funded by Sakura, which is one of the regions of IOOS. There really should be a whole bunch more people on here, and you'll see as we go along that we're using contributions from a lot of different folks across the geoscience community, both here and abroad. So I'm going to jump in here and tell you what I'm going to talk about instead of water levels. This just came up a couple of days ago, and so it seemed more timely to talk about this because there's really no storms. There's no northeasters about to hit the East Coast. It's a quiet hurricane season, so water levels, they're important, but this will serve the same purpose. And actually, so we thought, well, okay, so instead of using our notebook for comparing water levels from models and observations, why not use it for temperature? And this came up because I was contacted earlier this week by one of the swimmers and organizers of the Boston Light Swim. So the Boston Light Swim has been going on since 1907. It's an 8-mile swim from the Boston Harbor Light out here all the way into Boston Harbor. So this is actually from a GPS wristband that one of the swimmers had last year. It is 8 miles, and actually, so this is the lighthouse out here. See those kind of weird things in the distance? Those are actually the sludge digesters at the sewage treatment plant here. So it's basically twice as far as those tanks are away. It's a long way, and more importantly, or maybe equally importantly, there's no wetsuit. And if any of you have swum in the Gulf of Maine, you know that it's pretty chilly. So whether, if it's 62 degrees, they're pretty good, although 62 degrees is, for me, I want to jump in the water and just jump right back out again. But they're good at 62 degrees. If it gets down to like 54 degrees, then they have some problems, and some people may choose not to race. They have to monitor everybody very carefully and make sure that they finish in time. So they really wanted to know how cold the water would be on Saturday, the day after tomorrow, when they start this race at 7 a.m. So I said, hey, no problem. We've got these IOOS forecast models, and we can predict the water temperature for you. So I did that. I used an IPython notebook that we had to just grab some data from OPeNDAP and plot it up. They like these currents too, of course, because the tidal currents rip in and out of Boston Harbor. But they looked at these temperatures that were produced, and they said, oh my God, it's going to be 53 degrees. And I said, that's what the model says. and they said, well, let's check what it says today. They told me, you know what, this model it seems to be under predicting the temperature. The temperature seems today, when they actually looked at the nowcast result instead of August 14th, when they looked at today, they said, well, actually it looks like the water's warmer than that. So we said, this was a couple days ago, and we said, well, let's run our little notebook that compares the different models and see which models are doing better, and if this is a consistent thing, or try to find out a little bit more about what's going on here. So with that, I'm going to back off a bit before I show you that notebook and just make sure that you know that what IOOS is. I think most of you guys do, but it's, it's 11 different regional associations, 17 different federal agencies, all working together sort of across state and academic lines, trying to make the most of observing systems and oceanographic models that are running in different regions to solve local regional problems. And so the reason I'm participating in this is not only because I care about, I'm an oceanographer and I care about, I think this is kind of a neat idea, but also because it represents, I think, sort of in a microcosm, all the issues or a lot of the issues that we face across the geoscience community in terms of dealing with different types of unstructured and structured grid model output, data from different sensors, and trying to put that all together into some kind of system that's easy and effective to access. And I should mention here that this, specifically when I mentioned before that Secura was funding this, Secura specifically has funded a model skill assessment project. Deborah Hernandez and Vembu Subramanian have put forward funds that are funding Felipe on that. So, what kind of data are we dealing with? Well, actually, first of all, we're dealing with different observations and models, which I'll get to in a second. IOOS basically says if you want to play in IOOS, you have to provide web services, standard web services. So that's the only thing that they are going to allow you to supply. So we have that advantage in terms of being able to have standard web access services. And the data that we're serving can look like these curvilinear grid models in coastal regions that have these curvilinear coordinates like this in the horizontal, and they have these stretched vertical coordinates. So we're not dealing with rasters, right? We're not dealing with just satellite imagery or things that have fixed Z levels. You have to provide the full 2D latitude and longitude arrays, and you have to be able to compute these vertical coordinates. And that makes dealing with this data in an interoperable way a little more tricky. We also have these unstructured grid models, triangle-based or tris and quads. This is actually the New England forecast model around Woods Hole. I'm speaking to you from the Woods Hole Research Center right about in here. And we also have data from buoys, ships, gliders that we have to deal with. So we have time series and trajectories, as well as structured grid and unstructured grid. Luckily we have the CF conventions that help us actually come up with a way of standardizing how you represent all that kind of information. The OGC conventions actually don't provide that for us yet in terms of the curvilinear grids and the stretched vertical coordinates, but the CF coordinates do. And the unstructured grid part, we have sort of extended CF with a U-grid convention for how to specify data on those triangular grids. So basically, we have these two types of data that we're trying to integrate here in these notebooks: in situ data, and the web service that IOOS approves for in situ data is the Sensor Observation Service, OGC Sensor Observation Service, and for gridded output, like the model output, we have these OPeNDAP+CF conventions, and deliver those through OPeNDAP. And the encoding for the OGC Sensor Observation Service is XML or CSV. So I'm not really going to talk about web map services today. Okay, so I think that most of you know OPeNDAP, but I just wanted to kind of, if you're not familiar with Sensor Observation Service, it looks a lot like the other OGC services in terms of it has get capabilities. It tells you about what the service has. And then but one thing you can do with Sensor Observation Service is you can say describe sensor and get some metadata about the particular sensor before you go ahead and get data through a get observation. Any questions at this point, actually? Okay, I'll keep on moving. We make a lot of use out of the Unidata Threads data server, and we put both piles of files from models over here, as well as from buoys and gliders and things like that. We can aggregate and standardize those piles of files through NCML, the NetCDF markup language. And the Threads data server understands NCML because it relies on NetCDF Java to get all that stuff into a common data model. So we have a common data model for grid, for UGrid, for time series, profile, trajectories. And then once you've got these data in the common data model, Threads provides a variety of services that either Unidata built or have been built by others, so you can deliver the data out through OPeNDAP+CF conventions. But if it's SOS data, the data amenable to SOS, like time series or profiles, you can use SOS to serve them out through sensor observation service. And you can also, thanks to the work from NGDC, you can also get ISO metadata out. It converts the attributes in the NetCDF files or in the NCML into ISO metadata, which then can go into catalog services like CCAN PyCSW, GeoPortal Server, GeoNetwork, GICAT. So you get the metadata out, and then the services, of course, you can consume with different libraries. Of course, NetCDF Java understands the OPeNDAP+CF conventions for Java-based applications, and actually NetCDF for Python doesn't understand CF, but actually IRIS, the package IRIS, which I should have put on here, does understand CF conventions. I'll talk about those in a second. So with that, we have all our services. So that's one Thread server, but we have many Thread servers across the IOOS landscape. And what happens is the Thread servers, as well as SOS services that are not from Threads, like there's another database-driven SOS software called 52 North that provides SOS capabilities for some of the IOOS providers. The data, the metadata gets harvested nightly from these different services and transformed, if it needs to be, into ISO, if it's not ISO already, and then it goes into a GeoPortal server where you can access it through CSW. And then those different downstream sort of web-based applications like the IOOS catalog then can populate their what you see, in your web client by doing a CSW search and finding out all the data sets that are available. So we're going to take advantage of that too. If you go to the GUI, if you just go to NGDC's GeoPortal, you can search through all that metadata by doing things like NICOS or SOS and star temperature, and get back a bunch of data sets. And when you get back these data sets, they have, this is just the metadata being represented here. Is just the title and the abstract, and then the different service links appear here, in particular OPeNDAP or SOS. And here I've clicked on this one particular model output, and it's highlighted over here. So you can search on time, and you can search on space and keywords and stuff like that. But we don't really want to use a GUI because we're nerds, right? We want to access this stuff programmatically. We want to be more effective. And so I'll show you how we're going to do that in a second. So everything I'm going to show you today is Python-based in terms of access. We do have some, there's people who are using R and MATLAB and stuff, but Python is it's just a really nice environment for doing this kind of work, and the Python notebook is really proved super useful. So in terms of reproducibility, giving somebody an IPython notebook has been really helpful. So this is an IPython notebook that demonstrates getting data using OPeNDAP and with CF, and it's so IRIS is a project that's from the British Met Office. You can barely see that here, scitools.uk.org. And this is what provides the CF capabilities for NetCDF for Python. So we can open up one of those URLs that's an OPeNDAP URL, and yet it understands what the latitude and longitude coordinates are, and is able to you can just say load, get some cubes, look at them, extract some data on lat, lon, and time, and plot it up. And for For SOS and CSW, we're using the OWSLib library from Tom Kurlitis, and Tom works for Environment Canada, I think in the MAT area. And this is sort of, this library supports WMS, WFS, WCS, and SOS and CSW. So we make a lot of use out of this. It's been a great package. It's also had a lot of contributions from other folks, not just Tom. As you can see here, probably he didn't make all that money. So with that, I'm going to jump into this notebook. Oops. Okay, I'm going to let's see, jump out of here. I'm going to go right to this notebook here. So we have a notebook here that tries to basically use all those tools that I just showed you to find all the data that's in a particular region. Well, I'll just walk through it. Okay, so I'm not going to worry about stuff like importing pickle. I'm just going to highlight. I'm going to make this a little bigger. So this is a notebook actually that's running on Wakari Enterprise, which is that means it's running remotely. The server's running remotely. I'm typing in my web browser. I'm communicating with that server that's actually down in Louisiana. And it's a pretty powerful machine, so I like computing there. And there's a lot of data that I use that are big data that I use that are there, so I'm computing close to the data. In this case, I'm just pulling data from around IOOS. But and this was and Philippe actually did basically constructed most of this notebook using and fixing the original water level notebook that I had starting about a year ago. So basically, the user comes in and specifies, that they want to get data. You want it now, and the start time will be now plus 4, and stop of time of start 4 days before and end 4 days later, and a bounding box here for some region that you're interested in, with a little extra space to look for data nearby. And because we're going to give it some tolerance to be close to the model output. We want to look for seawater temperature, but this is a sneaky little function here, CF names, which is actually going to basically use the names that all the names that we know of that constitute seawater temperature. And this is going to convert everything into Celsius, and then basically with that data, we construct a filter. Okay, and we're going to search this endpoint here, which is the GeoPortal. Can you see this? Okay. Can somebody unmute and just say yes?
Yes. Yes.
Okay. Or you can say no too. But you can't see it. Okay. Okay. Let me just go one step up. And I'm hoping that everybody on this call is nerdy enough to like to look at code. That was an assumption I made. So we specify the endpoint, and then we feed it this. So we open it up, catalog service web, and we get records based on a filter constraint here. Constraints equals filter list. Okay, and this filter list we've built just above here. And what this filter list is it says, I'm going to look for either or any of the names in this list which have a property. Property is like, so the property you're looking for is like any of the names in this list. They can be any of them. So right, if you have seawater temperature, seawater potential temperature, and any of these number of names. You're going to say we're going to filter on any of those, but we're not going to take anything that has averages. So here we're doing so we basically what we did was we did this first, right, and then we said, oh gosh, we've got some files that are just averages of the other files, and this is kind of a standard thing that's going to happen, right, when we do catalog, when we have catalog-driven workflows, we're going to get essentially like duplicates and stuff, or maybe like filtered versions of the exact same data. And we're going to have to deal with them somehow. You might think that you're going to deal with them by querying the metadata, but I personally think, we're going to get, 80% of the way there with standard metadata, and then we're still going to have to do stuff like this in our workflows, just to pick out some of the stuff we want or don't want, because we're just never going to get there with we're never going to have 100% metadata for everything that anybody would ever want to do. So anyway, so then we say we have a bounding box, we have a start time and a stop time, we have a bounding box, so we AND all that stuff together. So we have stuff inside the bounding box, inside that time range that has any of those names, but not this name. That's a pretty sophisticated query. We do that query, that CSW can handle it. We get back all the data sets that match that. We then get the service URLs from those data sets because we're looking for SOS services and we're looking for DAP services. And then we basically try to figure out whether, so this is the sort of the part of the, I guess the rant part is that, we have to do a lot of work still here to kind of figure out what is a station and what isn't a station. Like the metadata is supposed to have in it, if you're fully compliant, it's supposed to say whether you're a model output or not, but a lot of data doesn't have that, and so we're trying to figure it out in other ways. Actually, incidentally, there was a really nice talk yesterday on a DMAC webinar that was recorded about the CF compliance checker. So there's a more sophisticated CF compliance checker that's been built under IOOS funding, and it has different sort of profiles. It has sort of a plug-in kind of thing where you can have it check for different types of attributes and things like that. So it can check for ACDD attributes. It can check for compliance with, I think, the NODC templates and things like that. So you might want to check that out. And if anybody's interested, just maybe somebody could chat. Somebody who actually could chat that into the chat here, or just ping me after, because it's pretty good, pretty interesting stuff. So that can help you actually figure. That would make our lives easier if people actually had compliant data. And here in this part, we're accessing the data from SOS, and here's another little ugly bit that you see where from PyUse collectors import NDBC SOS. You should be thinking, what? Wait a minute. Why do we have a standard service called SOS if we need to have a special function called NDBC SOS? And the answer is that these things are not. Also, these were old services, NDBC SOS and the NODC SOS were both sort of set up before, or the collapse SOS, sorry, were both set up before with SOS was really kind of standardized. And so these are like little helper functions that basically standardize those things for us. But at least the guys who wrote this had an easier job. Any questions on this stuff so far? Okay. Hopefully everybody's not reading their email now because they didn't really want to look at this code. Anyway, we're going to get to the result pretty soon. But so here's the code. Here's the COOPS SOS. So basically we're going to pull data. We found these. We found these different stations, and we're going to pull data from them. And then we're going to basically look for model output. I'm just going to skip down here. So here are these different stations that were found, and now we're going to look for models. And yeah, I'm not going to go through all these details, I think, in the interest of time. But we have to do some things like try to figure out what the surface layer is, because sometimes in the models, the layer 0 is the surface, and sometimes the last one is the surface. And then we're going to use Iris here to load the data. And we're going to actually look for data that's within a certain distance of each station. So if we find data within a certain distance of the station, we're going to extract a time series from that model, and compare it, and then we're going to interpolate it all. We have it in basically have it in a data frame, a pandas data frame, so we can plot it up, or do whatever we want, and or we can write. What we do here is we just write them out to little NetCDF files. And so I think I'm going to jump to actually just showing you the result at this point, and then you can ask questions about it. Get out of there. Thank you. Okay, so this one, this just loads the data. Actually, I skipped a skill score step where Philippe does nice things like calculates target diagrams, Taylor diagrams, and stuff like that. But I'm just going to, this basically, I'm not even going to show you this because all it does is basically loads up the data and creates this nice little folium map here, which shows you which data. I guess I have to reduce my, well, let's see. If I just zoom out, I guess. Okay, let's zoom out some more. So this is, this is kind of cool, right? So this is a JavaScript plot being generated by Python within an IPython notebook data frame. And the plots have also been calculated by Python, but they've been converted into little JavaScript plots. So you can see there are two stations here. We found 4 models here in Boston. This is where people care about, right? So let's take a look here. If I click on that spot, it should come up with the different plots. Okay, so here's a JavaScript plot again of this time series that we found. So we found 4 different models, or 4 different data sets. The observational data, it's a little bit hard to see with this legend here, but working on that. Philippe is working on that. But anyway, this observational data is the purple line here. Okay, now we're in Celsius. So 18 degrees C is that's fine. They'll be happy. They'll be happy with that. That's about 64 degrees or so. And what you can see here is that model we were looking at before. It's always cold. It's been cold. It's going to be cold. That would not be a good forecast model to use. And it's interesting, right, because this is our forecast model for New England. This is the highest resolution IOOS forecast model we have. You'd certainly want to use it for currents, but its temperature is way off. You know, it's like 10 degrees, almost 10 degrees Fahrenheit too cold. And look at this. Here's another model, a forecast model, the operational model we have running. This is actually a model we're running here at USGS. Its objective is not to predict sea surface temperature, but it's interesting that it's 6 degrees too warm, so it's way too warm. And you know, the actual model that's doing the best. This little green line here is actually interpolated SST data, so that's actually more data. And this blue line here is a larger scale model that the New England, the Syracuse region of IOOS is running, and it's doing pretty well, actually. So the large scale model that we ordinarily wouldn't have thought of using, because it actually drives this model, is actually doing the best. And so, you know, I think this is kind of cool for a couple of reasons. One is that it basically showed us, hey, we've got some issues with these 2 models, and it's not what we, you know, thought the answer would be. And yet, and it's also useful for the swimmers because we can tell them, hey, look, you know, over the last 2 days, it's actually gotten a little bit, it's going to get warmer. The models are not predicting some big, huge dip in temperature on Saturday when your race is going to run. And so, you know, it's pretty, we feel pretty confident saying that the water temperatures are going to be above 64 degrees or 18 degrees C, whatever that exactly is. So, you know, it's kind of a success in that regard, and it's also a success because I just want to, I'm going to, actually, before I jump out of this, does anybody have any questions about this stuff? The notebook stuff?
Rich, I have a question. This is Eugene. I have a quick question. You showed 2 notebooks. You showed the first notebook that you went through the code, and then you stepped into this tab. Are these separate notebooks?
Yeah.
Okay.
Yeah, so this is one notebook, and this is, there's one notebook that we have to fetch the data, and another notebook we have to do the skill score, and then we have another notebook to create the map. But, you know, they could be all strung together, right? It doesn't matter, but it's just kind of convenient to have one that fetches the data, and then you can mess around with skill scores, right? And then you can also mess around with the plotting without doing a bunch of complicated logic in your one single notebook.
Okay. Thanks.
Hello. Hi, Rich. This is Lee. Can you hear me?
Yeah.
My question is, this real-time data collected from the sensors?
Right.
And the model was run whenever you send the request, the SOS request. The model will also be run and show the results on the same plot.
Well, okay. So the observational data here, you can see today is the 13th, and the observational data stops. Well, pretty much now. And so this was pulled from the SOS server, a few minutes ago. This model here was run. These models are mostly run every night, and they forecast for several days. So you can see this one actually, the models, they're actually struggling a little bit with this model, and it hasn't run today, so it's not predicting anything during the race period yet. That should happen sometime later today. But the model that forces that model has already run, and so it ran this morning, starting here, and produced a 3-day forecast out to here. This model runs every day, but it only produces a 1-day forecast.
Wow, this is really cool. Yes, thanks. And I probably will contact you later after this meeting, talk more about the SOS service. Thanks.
Sure. So, I just want to emphasize that if you went back, well, okay, let me just keep on going here. But there's nothing in here specific to this region, right? You could just change the bounding box and look at something on the West Coast. In fact, this came from Philippe had a notebook that he was working on in Sakura that we just adapted for to do Boston, because that's the idea behind all this, right? It doesn't, you don't have to do anything special. That's the goal anyway. Okay, so that's I think I'll just stop. Oh, there's there's another station out here. This is an NODC buoy, and here it's actually kind of interesting because I'm not really going to. This isn't really a science talk, but it's just kind of interesting that that model that was so bad before Coast, now it's actually tracking the observational data, which is now in yellow, or that kind of yellowish color, pretty well. And so the Coast model is actually doing okay offshore, but inshore it's not doing very well at all. And that the model that should be doing the best is still doing terribly. The model that has the highest resolution. And here it's kind of interesting because you can again see that now we got HICOM coming in. So HICOM is only once a day, but it's not too far off. And of course the other models are the same. So let me jump back to the presentation here just to finish up. So that was cool, right? But what if you want to do this yourself? Because it's fun to watch me do it, right? But it's really the main point of this is to make something that anybody can use. And so what we've done to help facilitate that, and again, largely Philippe. Actually, before I show you that, I just want to show you what we found out. Based on this, we actually went and looked at that, those two models, the lower resolution one that was doing well, that has sort of temperatures in the 60s here in Boston, which looks pretty good. And then we looked at the high resolution one. So this is the parent model, and it's driving this child model. Wow. So the child model, it's being driven on the boundary with the parent model with the correct temperature, but the interior is way too cold. And it turns out that in the other model, we over the last 2 days I've been talking with the modelers, and this model assimilates sea surface temperature data, and this one doesn't. And so basically it means that the sea surface temperature must be covering up for a lot of sins probably in the shortwave radiation or something else that's resulting in this water just getting way too cold. Anyway, science tidbit. Okay, so what have we done to make this easy for you to run? So I would like you to be able to go just run this yourself after this webinar, and you can. You should be able to. If you Google on our Signell-USGS or OSEF path, Philippe, are you on the line? He might not be on the line. Okay. Well, anyway, I still don't know what OSEF path means, but anyway, that's Philippe. And GitHub, you'll find all this stuff. And in fact, at Philippe's GitHub site, you'll find the Boston Light Swim repo, which has the instructions for how you install this yourself. And you can really do it, and you should be able to do it in less than 15 minutes on any platform. But we might have a Windows issue or something right now. I'm not sure. Oh, I think there's some Windows. Yeah, so there might be some Windows issue with closing files or something. Something's supposed to be part of standard Python that doesn't work in a standard way on Windows or something. But everything we've built, so what we've done is everything that needs to be, every package that you need in your environment to run that notebook, and there's a lot of them, we have distributed on this anaconda.org IOOS channel. So we have 144 packages here, and they're built for Windows, Mac, and Linux. So they, if you want to run this notebook, it's one thing to have a standard so you can access the data. It's great. That's fantastic. It's also, we also, for reproducibility and shareability, we need notebooks like, we need to see the code, right? So we need the notebooks, but then we also need the environment. We need the computing environment to run the notebook. And that involves all these lots of sort of packages that may be easy to install, may be hard to install. And this has been sort of the bane of, a lot of people started trying to use Python and got frustrated because they have packaging problems. They couldn't get something to run on their, Mac OS, and that somebody else on Linux could. And anyway, this has solved a lot of problems. Having a place where you can build binaries, packages that you can just install and run. And so all of these exist, almost all of them exist on every platform. And so if you go actually the Conda on GitHub and under the IOOS channel, under Conda recipes, you can see how we build all these packages. And on the wiki there, you can there's instructions that we give people when they say, hey, how do I install Python? We say, do this. And it's got instructions for downloading the free Anaconda distribution, and then installing all the packages from our IOOS channel that you need to run these kind of notebooks. Oh wait, I'm not really in presenter mode, am I? Let me jump in there. Okay, so on this, again, just there's instructions here for the different platforms, and if you have an issue, you have any problems here, you can raise an issue and say, hey, I stumbled a bit. What's going on? And we'll try to help you. So, in summary, we've got standards, services, catalogs. They all help us serve data in a unified way. And Python and tools like it give us free scientific access, analysis, and visualization environments, which we can use to do searches, access the data, do analysis, make the plots. The notebooks give us this sort of documented workflow so that we can just hand you a workbook. You can see exactly how everything works. You can also, as I was sort of mentioning, you can use it from your browser. You use it from your browser. You can have the server running locally. If you follow those instructions, you'll be running your own notebook server. But you can also take advantage of people who have set up servers that are running at other places like, oh yeah, this was a joke. Yeah, I wanted to have the Windows update pop up in the middle of my presentation. Okay, so it's really cool to be able to do the computations in the notebook really close to the data when you're dealing with big data. So we use that in the IOOS Coastal Ocean Modeling Testbed. In this case, we're not using that, but it's just a cool feature. So Anaconda and Anaconda.org really are super useful because it really lets someone in about 15 minutes just duplicate your whole environment, install Python, and set up an environment that has all the packages that you need to run that particular notebook. And in the end, I think you get more efficient and effective access to ocean data and make it possible for anybody to really do this kind of assessment. And I think that's really huge. When we get people like ocean swimmers, running, in a notebook, maybe we make a nice little, interface to that kind of notebook, or make it really simple for people to modify it. But actually, the swimmer who I've been working with, I shared a notebook with him on Wakari, and he just logs in and he changes the bounding box. He doesn't understand any of the code, but he can change a bounding box and he can change a time. So he's been looking at different offshore swimming locations using these tools. So I think it's, and of course we could put turn them into just regular Python code and put a nice little front end on them or something. But anyway, that's the reproducible workbook story. I'll take any questions.
Thanks, Rich. That was great. I have a quick question to start things off. So the Anaconda.org and the IOOS channel or whatever makes it really easy to install everything you need locally anyway. Is that the case for, what about in Wakari? How do you set up a Wakari environment with all this?
So if you're using just like the public Wakari, you can open up actually either one. I mean, we're using the public Wakari is a little bit can be a little bit flaky, but it has the advantage of being completely free for now anyway. But in that or Wakari Enterprise, which we're also using on the test bed, you just open up a terminal, and in the terminal you just type the same commands that you'd type if you were installing it on your local Windows or Mac or Linux machine. It's the same thing. So you just create a new environment, and you say conda create -n, and you create a new environment, and then you can switch in Wakari. You can just pick which environment you want to run your notebook in.
Okay.
Philippe, are you on the line? Okay. Are you muted? Or maybe is your internet connection so crappy down there in Brazil that you can't talk? No audio. Okay. Well, I was hoping Philippe could talk about all, mention all the stuff that I forgot to talk about. But anyway, I mean, it really is not. It should be clear that it's not really limited to ocean data either, right? I mean, that all that same stuff would work for any of the MET. Oh, actually, I know what I wanted to. Well, are there any more questions? I did want to say one more thing about if, like, you wanted to implement this yourself.
Yeah, actually, I had a question, Rich. It was about when you were accessing the CSW web services. So I'm assuming they were web services, anyways.
Yeah.
And so you were querying the catalogs and doing some pretty sophisticated stuff, and it kind of zipped by me. Partly because I was looking at some other code. Sorry. I like code. It wasn't email. But anyway. But I wondered, so where are those CSW servers running? And how do they correlate with OPeNDAP and SOS data source, the data that are accessed through OPeNDAP and SOS in this example?
Yeah. Okay. So CSW basically is, you're obviously like any other OGC service, you're free to, develop it the same way, just like you guys have developed your HIRAX OPeNDAP and, Unidata did their Threads OPeNDAP. It's just a service that different people can set up. So there's different implementations of CSW around, and so if you install a GeoPortal server, like the one I was showing, it has a CSW interface. You can install PyCSW, which is a Python-based CSW service, which actually I was going to mention because if you thought, oh, I'd love to do this, except wait a minute, my stuff is not in this IOOS catalog, right? You'd say, hey, I have a bunch of folks I deal with who have HIRAX and Threads, servers, and I just want to bring in all that metadata and put it in a database and search it with CSW. Well, PyCSW is a really cool thing that I actually I use it when outside of IOOS, and it's super easy to set up. It's all Python based, and it installs in like 5 minutes. And I don't know anything about databases, and it's all command line driven. But if you do know about databases, you can connect it. I think it uses SQLite or something as a default database. You can hook it into other databases, and so basically you're querying a database of metadata. So PyCSW, you create ISO metadata, or you can. So actually, what we do a lot is we crawl our Threads catalogs or HIRAX catalogs and extract you can actually point NC-ISO. You could run NC-ISO on its own and point it at any OPeNDAP or any kind of threads catalog, and it'll crawl the catalog, produce ISO metadata, and then or if you have the ISO services running, you could just crawl it with a threads crawler and extract the ISO metadata that way. So you have all this, you have a collection of ISO metadata. PyCSW, you run PyCSW and it sucks up that ISO metadata, sticks it in the database. You do CSW request, and it it returns metadata. But in the metadata are the service endpoints, OPeNDAP and SOS, stuff like that. So that's the holy grail, right? That's what that meant to me, is that we go, in the future, we go to data.gov, we do these CSW requests, we get back our OPeNDAP links and our CSW links and our WMS links, and we do cool stuff with them because we know what these things are serving. The services are, working as expected, and the metadata is sufficient enough that we can do cool, stuff driven by a catalog search of, at the beginning. Because I didn't even know that SST product existed. It just came in on the catalog, when we queried. And
that's pretty intense.
Yeah, and we were doing water levels. It would be like, I was looking at 3 water levels one day, and I ran my script again. Another one popped in because somebody registered their model. I had no idea that they had a model, but it popped. It's just so it's cool.
That is, so I have a couple more questions about CSW. Yeah. I don't want to monopolize the meeting, though, so maybe if other people want to, I'll make them brief, and you can either say I'll answer it offline or whatever. But do you know if there's a way for CSW to assimilate stuff from remote CSWs? Like, for example, can a centralized CSW be told there are these 1,500 CSWs out there, just go get their stuff? Do you know if that's possible?
Yeah, it totally is,
Yeah,
that's called federated, and you can actually, that's a federated search, right, where when you actually do the search in one CSW, it goes out and searches other CSWs. Or you can also just have them harvest from other CSWs.
Yeah, I was actually talking about the latter, but both options are pretty interesting.
Yeah.
So CSW can certainly be populated with the kind of information that comes out of the combination of threads and NC-ISO. Is it correct? Is that what you're saying?
Absolutely. Yeah, that's exactly what we're doing. I mean, the only thing is that, you have to, basically, the most important things, obviously, are having the, the latitude, longitude, latitude, longitude range, time range, the list of, with the variables. But, of course, that just comes from an OPeNDAP data set, right? It can calculate, with CF conventions, it knows enough. NC-ISO can just calculate those ranges even if they're not supplied and create the metadata elements that describe the extents based on the data.
Right. Yeah, that's pretty cool. Wow, that is kind of the holy grail, or it's getting grail-like. So if Unidata and OPeNDAP and maybe the ERDAP folks too, if we were all to start supporting CSW endpoints in the servers that we're releasing, that might push this whole process along quite a bit faster, huh?
Yeah, you don't have to support a CSW service, right? You don't have to do anything, really. You're already supporting, it's really anybody can start up, or maybe you're saying as a community, we could start up a CSW that people could register their different threads or high racks or SOS or ERDAP endpoints, and something larger than IOOS maybe, but smaller than data.gov or something.
Yeah, something along those lines, although I was also thinking in particular that a server can crawl its own local holdings far faster than something out on the web can crawl.
I see. Okay, so I see. Create a folder of metadata that people could just access.
Exactly, and since there is this sort of federated and harvesting mode to CSW, then you could have various kinds of centralized ones, and they could be told just go to this place and harvest it, or you can federate to it. But if you've got potentially hundreds of thousands or millions of granules behind one of these servers, it's much nicer to crawl them there than it is to try to crawl them over the web, because that can take weeks or months.
Actually, you know, that's actually a good point. That was one of the lessons learned on in the IOOS experiments, was that it's much more effective to have people create their own, different organizations create their own web accessible folders of ISO metadata than to try to crawl everybody's threads and hierarchs and whatever services every night, because not only do you end up, each group can say, hey, wait a minute, you know, I actually don't want to, you know, read the 1,000 granules that are actually part of this aggregation. You know, they can be more, you know, they can be more skillful in the in crafting the ISO records that they actually want to have consumed, and then you know, then you can just basically register the web accessible folder endpoint of ISO metadata, and that's much more effective. And then there's much less work for the centralized, you know, gatherer to do. It's easy to read ISO metadata. It takes more time to crawl a catalog and, you know, read data to compute extents and stuff.
Exactly. Yeah.
I was just going to mention that I think Philippe and typed in some stuff in the chat. It's too noisy where he is to turn on his mic, but he did want to say that things should work, and all these notebooks should work on Windows now.
Oh, okay, cool. I mean, you know, that was a little bit. I'm glad he's chiming in on that, because you know, there are. I don't want to make it sound like it's really cool that there's so much stuff that works on Windows now that I mean, basically everything works on Windows that used to, you know, there used to be a lot of stuff that didn't work very well on Windows. And in the last year or so, I think the combination of being able to build stuff on Anaconda and kind of folks teaming together who know how to build stuff on Windows have really made a huge difference. And you know, you should be able to run anything on that IOOS channel on Windows, and that's great. So yeah, actually, I'm going to go try that after this telecon. But please give this stuff a try. I guess I just want to say that, you know, try running it yourself. Just try running exactly that same notebook, but then try, you know, going to a different region and running it. Try, you know, looking for salinity or do something else. You know, modify it, and please, if you do run into issues or you make improvements, just raise issues on GitHub, and it'll, you know, we'll build a better world together.
Great. Well, thanks very much, Rich. Does anybody else out there have more questions? All right, I'll make a plug for the rants and raves and say if anybody else out there has ideas about who or what should be presented or wants to present something, please let me know. This is Ethan, by the way, and my email is edavis@ucar.edu. If that, so let me know.
All right, thanks a lot, Ethan.
Yeah, thanks. I guess. Eugene, I see you just popped up. Do you have a question there, or?
Oh, I just want to say thanks. This is great. Very
all right. Nice. All right. So I guess we can sign off, and thanks again, Rich, for a very great presentation.
All right. Thanks, everybody. See you later.
Yep. Thank you.
Thank you, Ethan. Thanks. Thank you. Bye.